Okay, so now we're going to talk about salts. And I know the first thing you think of when you think of salts, you think of NaCl. And you would be correct, NaCl is a salt. But a salt is an entire category or classification of chemicals. Just like acids are a classification and bases are a classification. And a salt is the product of an acid-base reaction in addition to water. So maybe you remember doing double replacement reactions. The NaOH and the HCl produce water, and you have NaCl left. It is the ionic product of an acid-base reaction in addition to water. Okay, because it comes from an acid and a base, depending on how strong your acid and base are, it can affect the pH. The salt can affect the pH of the solution. If it's a neutral salt, it has a pH of 7, and that's because from a strong base and a strong acid, the conjugate base, conjugate acid of those are too weak to react with water. So it is completely neutral. Basic salts have a pH greater than 7 because the cation of the strong base is too weak to react with water, but the anion coming from a weak acid can force water to act as an acid and donate a proton, and it changes the pH. Okay, acidic salts have a pH less than 7 because the anion of a strong acid is too weak to react with water, but you have a weak base that can force water to act as a base, and it produces H3O+. So in order to determine the kind of salt you have, you need to identify what acid and base created it. This by far is the hardest part of this lesson. It's the hardest part of this chapter, okay, is trying to identify it. I am familiar with it because I have done this so much and I've practiced it so much and I've taught it so much that I'm very familiar with it. And for you guys, never having really done this before, it's going to be a challenge at first, but you'll get the hang of it. You'll start to see a pattern as we go. All right, so let's talk about basic salts. Basic salts exist when you have a weak acid turn into a conjugate base, and it will react with water and it will determine the pH. The way you know is if you have a weak acid plus a strong base, you get a basic salt, and so I'm going to abbreviate it BS, and that's what it stands for, is basic salt. When you have a strong base like NaOH and a weak acid like HF, these guys turn into water, these two together turn into this, and this is a basic salt, the product of a strong base and a weak acid. When the NaF forms in water, the Na plus is much weaker than water because it came from a strong base, so it's a spectator. The F minus is a stronger base than water, and it can force a reaction. If it is from something strong, it's a spectator, and we are going to eliminate it. So when I write the reaction, I'm going to take the Na part out, and all I'm going to have is F minus reacting with water, forming HF and hydroxide. What happens is the water donates a proton, because that's what bases do, is they accept a proton, and you get HF and hydroxide. And this right here is why it is a basic solution. It's because it produces hydroxide. Okay, this right here is the conjugate base of HF, and it's important to learn to recognize conjugate acid-base pairs. And the conjugate acid-base pair would be HF and F minus. HF is an acid, it starts with an H. F minus is its conjugate base. Okay, and you should expect to get a pH greater than 7. Okay, so we're going to talk about how to calculate that, but in order to calculate it, you're going to need the Ka and the Kb of the original weak acid or base that you started with. So for example, any conjugate acid-base pair, in our last problem, our last equation, we had HF and F minus. These are a conjugate acid-base pair, and the difference between them is 1 H plus. The acid always has the extra H on it. So this is the base. And the way it works is Ka times Kb is 1e negative 14. So for the two of these, the Ka of HF multiplied by the Kb of F minus is 1e negative 14. Because they are a pair, they're grouped together. Okay, so if I have to find the Kb of F minus is just a simple algebra equation. So Ka times Kb is 1e negative 14. 7.2 is the Ka times the Kb. And to solve for the Kb, we divide by both sides by 7.2. Oops. And this goes away, and you get the Kb is 1.39 e negative 11. Okay? And you're going to need that anytime you have a salt. And you have to learn how to recognize them, and I'll show you how to do that. Okay. Now, to write the dissociation reaction of NaF in water, and they tell you the Ka, and they want you to calculate the pH. So first thing you have to do is you have to look at NaF, and you have to identify it as a salt. And it originates from NaOH and HF. And I recognize NaOH as being one of my strong bases. HF is right up here, and it's a weak acid. So strong base, weak acid is a basic salt. And what you want to do with a salt is you always want to eliminate the strong ion, the spectator. Whatever comes from something strong. My strong base is Na, I'm going to get rid of it. So to write my dissociation reaction, I do F minus, and notice that these two are a conjugate acid-base pair. The difference between them is 1H. I'm going to add water to it. And then I have to figure out what it turns into. And that's literally the hardest part of this, is knowing what your reaction is and what to figure out. Since this is my acid, and it's got a Ka, that means this is my base. So it's going to act like a base. And the H2O is going to donate a proton. Oop, go back. I'm not done there. And you're going to get HF. And if I take the H plus out of water, I'm left with hydroxide. Now, to calculate the pH, you have to learn to set up an ice table, and I think you guys are pretty good at that. The hardest part is writing the reactions. So ICE. Oh, God, why does it keep doing that? Big X here. F minus is 1 molarity, 0, 0, plus X, plus X. Oh, God, stop it. I don't know why it keeps doing that. You have X and X. I don't know why it's doing this. I'm sorry. And then 1 minus X. You're going to set it into 1 minus X. And so what you set it up, that's X squared over 1 minus X. That is the K. Oh, my pen changed color. But you have to recognize this is a base, which means I need the Kb, which is 1e negative 14 over 7.2e negative 4. Do your little assume X equals 0 with respect to 1. Solve for X by cross multiplying and taking a square root. Once you do that, you get X as 3.73e negative 6, and you need to recognize that that represents this and here, but in particular the hydroxide. So if you do negative log of that number, that is the POH is 5.43. Subtract from 14, and the pH is 8.57. Okay? The hard part is not the math. I know you guys can do these ice tables. I know you understand what they mean. I know you can recognize this. The hard part is that part right there. Okay, for an acidic salt, it's a similar process. It's a cation of a weak base and an anion of a strong acid. The way you do it is the cation from the weak base will be stronger than water, and it's going to react with it. Okay, the anion of the strong acid is going to be a spectator, so we're going to cross it off. And anytime you have a weak base, strong acid, you get acidic salt. And you should expect to get a pH less than 7. And remember, you need this as well. Okay, so for this one, first thing we have to do is identify what kind of salt NH4Cl is. And it's helpful if you look at this and you look at that and you recognize that NH4 and NH3 are a conjugate acid-base pair. The only thing that's different about them is 1H plus. And if Kb is the base, then NH4 plus is the acid. And Cl is the product of HCl, the strong acid. That means it's my spectator. So my reaction is NH4 plus water. Got rid of the Cl. Because this is the base, that means NH4 is the acid. It's going to act like an acid, and acids donate protons. You get H3O plus and NH3. And notice those two are both here. Conjugate acid-base pair. You're going to set up your little ice table. This is 0.4. It's doing it again. 0, 0, plus X, minus X. I think my marker, my little stylus, is going bad. Okay, so set this up. X squared over 0.4 minus X equals the K. Again, this is an acid. If it's an acid, we're looking for a Ka, not the Kb that's given in the previous problem. So 1e negative 14 over 1.8 e negative 5. Do your algebra. X equals 0 with respect to 0.4. Solve for X. 1.49 e negative 5, and that represents the H3O plus. So if you do negative log of that, you'll get a pH right away of 4.83. So I don't want you to get the idea that the pH of salts is closer to like 1 and 0, because it's not. Or closer to 13 and 14. It tends to be closer to the 7 range because they're not as strong as a strong acid or a strong base, or even as strong as a weak acid or a weak base. So they tend to be closer to the middle range on pHs. Okay, now here's how you identify them, and I'm going to have you guys add this to your notes. First of all, what happens if it's a weak acid, weak base? Not going to have to worry about that. So identifying an acid, that's in this column. They start with an H. There are 6 strong acids. HCl, HBr, HI, HNO3, and H2SO4, and HClO4. H2SO4 you will never have to do anything with. The only way to calculate the pH of sulfuric acid is to do the quadratic equation. And you might have to do that if you take college chemistry, but you will not have to do that in here. And weak acids have a Ka, but usually they start with an H. Bases start with a metal hydroxide. That means Li, Na, K, or Rb. All of them are positive ions. That's it. 4 strong bases. Everything else is weak. They generally have a Kb. A lot of times they have some kind of organic compound with N, H, and then some number. Could be 0. It could be like CH3N or CH3NH3. That's how you know. But they have a Kb. That makes them a base. Now the salts are the hard things. Salts start with Li, Na, K, or Rb, which is right here. Or they end with Cl, Br, I, ClO4 minus, and NO3 minus, which are your conjugate bases of strong acids, or they're both. They start with one, they end with the other, or they do both. If they do both, they are a neutral salt, which means the pH is 7, and I'll show you why in a minute. Okay, basic salts have the following formulas. They're a metal, Li, Na, K, or Rb, with some anion. And that anion is the thing that does the reaction. The metal ion is a spectator. We're going to get rid of it. So you only use the anion plus water in the reaction. Since it is a basic salt, this is a base. Water is going to donate a proton and produce hydroxide, and then an H plus stuck on my anion, whatever it is. Okay, but because it produces hydroxide, you're going to get a pH less than 7. You're going to do your little ice table. The big thing is you need the Kb. Okay, acidic salts have the following formula: some kind of RNHX thing, that's from here, but they end in Cl, Br, I, NO3, or ClO4 minus, which are my strong acid things. Okay, the anion is a spectator, so we're going to cross it off. You're only going to use this guy. It's going to have a plus charge, and you're going to add it to water. Water is going to accept the proton. This is an acidic salt. You're going to get H3O plus and RNHX minus 1. because it donated one of the protons to the water. Instead of having x, it's going to have x minus 1. I think I'm getting my marker too close to the bottom, my stylus. Okay, so now let's do some practice problems. We're just going to do the dissociation reactions. That's the hardest part. I'm assuming you guys can calculate the pH. So first of all, we're going to look at this, and I want you to look back at that chart and identify what it is. First of all, none of these are acids or bases because we're practicing salts. I have one where it's all mixed together. For right now, we have to figure out what kind of a salt it is. If I notice Na and Cl, Na comes from a strong base, NaOH, and Cl comes from a strong acid, HCl. This is a neutral salt. The way you write the dissociation reaction for any neutral salt works the same way. You cross off the spectators, which means they're both gone. Neither one of them is going to participate in dissociation. The only thing you have to participate in the dissociation is water. And when water does its dissociation, starts with 0 plus x, you get x squared equals 1e negative 14. X is 1e negative 7, which represents this, which is why the pH is 7. For pure water, it's also why the pH for a neutral salt is 7, because I got rid of both of them. They are both spectators. Okay? Let's look at this one. KCN. All right, look back at your chart. See if you can identify what kind of a salt it is. It starts with a metal, K. That is a strong base, KOH, and then CN. And if you look at this one, CN minus and HCN minus are a conjugate acid-base pair. Difference between them is 1AH plus. If this is the acid, this must be the base. So the reaction is CN minus, get rid of the K because it's a strong, add it to water. If that's the acid, this is a base. And it's going to do what bases do, which is accept a proton. You get HCN and hydroxide. And you're going to set up your ice table, but here's the big thing. You need the Kb of Cn minus. Okay. Last one, we have to identify what it is. You probably can guess from, process of elimination. But just to prove it, you look at this and you look at this. And I notice that the difference between them is 1H. So again, we're dealing with a conjugate acid-base pair. I don't know what it's doing. This is really annoying. I need to get a new stylus, apparently. All right, so from the current slide. So for this one, they're a conjugate acid-base pair. If that's the base, Kb, then this thing must be the acid. Cl is a spectator from strong acid, HCl. So your reaction is C2H5NH3 plus H2O goes to C2H5NH2. It donates a proton and H3O plus, and you need the Ka of C2H5NH3 plus. And it is the conjugate acid-base pair of this guy. All right? The only other kind of problem you're going to see is where it's like a multiple choice. And so on your notes, I don't think you guys have that line. I want you guys to add the word most acidic, most basic. And it's kind of a process of elimination. But if they're all 1 molarity solutions in water, let's see if we can identify and narrow it down a little bit. Okay, so let's look for some acids. The way you identify an acid is it starts with an H. I see 2 things that start with an H. This one has a Ka that you would get from a table. This one doesn't. This one is a strong acid. This one is a weak acid. So HCl is going to have the lowest pH. HNO2, though, probably has a pretty low pH, but not as low as that, not if they're the same molarity. So they're done. Now let's see if we can identify strong bases. Strong bases are metal hydroxides. KOH is a strong base. It's probably here. Now we want to look for something that's a weak base. Well, if this has a Kb, that tells me it's a weak base. So CH3NH2 is somewhere in that range. Okay, that one's done. Now we need to figure out the KCl and CH3NH3Cl and the KNO2. So let's look for the neutral salt. Neutral salts are made from strong bases and strong acids. This one came from KOH and HCl, KCl right in the middle. Done. Okay, now we have to look at those two. And I usually think it's easier to recognize basic salts because they always start with a metal and they don't end with hydroxide. So starts with metal, doesn't end with hydroxide. That is a basic salt. KNO2 goes here. This one, strong acid Cl. This is a weak base. Sorry, the conjugate acid of a weak base from that guy. So it goes here. That is the hardest thing, is identifying what they are. Once you can do that, you guys can do ice tables. I know you can. It's just a matter of figuring out what to do. Okay, and that's the hardest part.